Hello, my name's Thanom and I'm from UNSW. Today I'm working through some of the questions from MATH1011 Calculus in the differentiation section 2.3. So starting with this motion question, question 14, which gives us the equation of the displacement of a body that's moving in one dimension. So we have s equals 2t cubed minus 21t squared plus 60t. Presumably where t is time. So the first part of the question asks us simply to calculate s when t equals 3. So this is reasonably straightforward. We need just to plug in t equals 3 in here and work out what this value is. If we have a calculator, that's easy. If we don't have a calculator, we have to think a little bit carefully. Here we have 6 nines minus 21 nines, so that's minus 15 lots of 9. And then I guess this is plus another 20 lots of 9, so that's 5 lots of 9, which is 45. Let's just assume t's in seconds and the displacement's in meters also. I think that will be easiest for this question. So after 3 seconds, its displacement is 45 meters. The second question says find the values of t when the body's at rest. At rest means v equals 0. So we want the velocity as 0. So over here I'm going to draw the graphs towards the end, but my displacement equation I've written up here, if we want the equation for the velocity, that's the derivative with respect to time of this displacement equation. So 2t cubed differentiates to 6t squared minus 21t squared differentiates to 42t plus 60t differentiates to 60. So that's the equation of my velocity, which you can factorize. 6 comes out and we're left with t squared minus 7t plus 10, and that factorizes nicely as well into t minus 2, t minus 5. So that's my equation for velocity. So if I want to solve velocity equals 0, I'm trying to solve 6 outside of t minus 2, t minus 5 equals 0. So I know t is either 2 or 5, let's say, seconds. Okay, so the body is at rest after 2 seconds and after 5 seconds here. Part C is asking us for the initial velocity of the body. The initial velocity initially is t equals 0, right at the beginning at time equals 0. So when t equals 0, we have our velocity. Well, here's our expression for velocity. We can plug it into any of these. Possibly the easiest one is the first one, 6 lots of 0 squared minus 42 lots of 0. Well, all of that 0 plus a 60 here. So we're talking 60. Now it's velocity, so that means we're talking 60 meters per second. So that's its initial velocity, and after 2 or 5 seconds, the body's at rest. Let's put that together on a picture of the velocity. We can graph this velocity against time. We know this is a parabola that passes through 2 and 5. Now we know its initial velocity is 60, so it means it's starting somewhere at 60. So that means this is the parabola here. And we can see, so let's say that's 60 meters per second. So it's starting at 60 meters per second. The velocity is decreasing to 0 here. It's at rest. The velocity is still positive up here, okay, but it's just decreasing to 0, so it's still moving to the right. Then under here the velocity is negative, so it's stopped and turned around here, moving in a negative direction. It's at rest at 5, and it's turned around and then started to move in a positive direction. So we want to be able to interpret graphs like this, and these part B and part C make sense according to that graph there. For part D, find an expression for the acceleration at time t. Well, if I have my velocity is this expression, my acceleration is the derivative of that velocity with respect to time, or the second derivative of the displacement. So I'm going to differentiate this one. 6t squared differentiates to 12t, minus 42t differentiates to minus 42, and that constant 60 differentiates away to nothing. So we could take, I guess, a 6 out if we wished, and got 2t minus 7. That's slightly easier to handle. So that's my expression for the acceleration. So let's just write that down. So acceleration is given by 12t minus 42, or 6 outside of 2t minus 7. And if we want the initial acceleration of the body, remember initial means at the beginning at time t equals 0. So at t equals 0, our acceleration is 12 lots of 0 minus 42. So that's minus 42, and acceleration is meters per second squared. Meters per second every second. So what does our graph of acceleration look like? This is just a straight line. Initially it's at minus 42. So that's where we're starting, minus 42 meters per second squared. Now we can see that this intercept here is going to be 3.5, which is exactly halfway there. So this is a straight line that passes through 3.5 seconds here. So what's happening? Well, initially the particle is moving at 60 meters per second. But initially it has an acceleration of minus 42 meters per second squared. So that means it starts off at 60 meters per second squared, but straight away its velocity is changing at minus 42 meters per second every second. So that's why it's decreasing in its velocity. It's kind of got a force acting in this negative direction, decreasing the velocity to 0 here, right? So the velocity is negative in this direction. At this point here, the velocity, the change in velocity is 0. That's why we have this stationary point here, and this corresponds to the acceleration being 0 here. Okay, so we've answered all the questions and we've drawn some graphs for velocity. Let's just put together the graph for the displacement at the beginning. We can factorize this a little bit. We can take at least a 2t out and get a t squared minus, I guess, 10.5t plus a 30. Right. This is not so easy to factorize. In fact, you can't factorize it over the real numbers. But we can still work out what's going on because we have these graphs of its derivatives. So we know when t equals 0, the displacement is 0. So we know it's starting here. We know there's stationary points at 2 and 5. So here, this velocity is going from positive to negative. So that means the gradient of this is going from positive to negative. So this is a maximum point here. So at 2, there's a maximum point. And what happens is at 5, its gradient's going from negative to positive. Or its velocity, it's going from moving to the left to moving to the right. So at 5 somewhere, it's turning around like this. So a positive velocity, negative velocity, positive velocity means I'm moving to the right, I'm moving to the left, I'm moving to the right. And if we want, we can plug in 2 and 5 to get those values there for the coordinates of the stationary points. Okay, but I won't do that at the moment. Okay, so the main ideas is that we have an expression for displacement in terms of time that differentiates to velocity in terms of time, which then differentiates to acceleration in terms of time. We can draw the graphs and then we can see what exactly is going on with the particle in terms of where it's moving, what its velocity is, and what the acceleration of the particle is according to time. And so we can answer questions that ask us either to plug values in or to solve, for v equals 0, or perhaps we might want to solve for acceleration equals 0 or something like that. So that's question 14.